Hi everyone, this is Maverick Paul, the Chemistry Guru. Now sometimes during electrophilic addition reactions involving alkene, we do encounter the situation where we get more than one possible product. This is when our alkenes are asymmetrical and the reactants that we are adding is also asymmetrical, such as hydrogen halide, HBr, HCl, or water. So what we need to do is to predict the major product for this reaction, and we can use the Markovnikov rule for us to determine this major product. So let's take a look at this example. So we have this example here, my CH2 double bond CH bonded to a CH3 group. Now, you notice what we have is my alkene is asymmetrical because if I look at my double bond, this carbon 1 is attached to 2 hydrogen, while carbon number 2 is attached to 1 hydrogen and a CH3. So these two carbons, they are different. And later when we add asymmetrical reactants such as HBr, then we will have two different products where my hydrogen is attached to carbon 1 versus where my hydrogen is attached to the second carbon. Now, Markovnikov rule says that for our major product, the hydrogen will be added to the carbon with more hydrogen. So this rule is actually very easy for us to apply. It is also, sometimes we call this the rich gets richer rule, because the carbon with more hydrogen will end up getting more hydrogen. So what we can do to predict which carbon has more hydrogen is I can just box up my double bond. Then I have two different carbons, correct? So I can go and count the number of hydrogen attached to each carbon. You notice this carbon 1 has 1 hydrogen and 2 hydrogen. So the carbon on the left hand side actually has 2 hydrogen. Then the carbon position 2, it has only 1 hydrogen and 1 R group. Now take note, I have 3 hydrogens here, but these 3 hydrogen actually belong to carbon 3. It doesn't belong to carbon 2, so we don't count it as my hydrogen. So this carbon 2 only has 1 hydrogen here, so this has 1 hydrogen. So if I compare between the two, carbon 1 has 2 hydrogen, carbon 2 has 1 hydrogen. So obviously carbon 1 has more hydrogen. Then according to Markovnikov rule, hydrogen will be added to this carbon to give us our major product. So we have this product here. If I'm adding HBr to this alkene, then this will be my major product. You notice my hydrogen is added to my carbon 1 because carbon 1 is the one with more hydrogen. Whereas for Br will be added to my second carbon. So this compound we have drawn is the major product. And of course, we can draw our minor product. It will just be when my hydrogen is attached to the carbon with less hydrogen attached to my carbon 2. Alright, so this is our minor product. You notice when my hydrogen is attached to my carbon 2, the carbon with less hydrogen, and when my Br is attached to carbon 1, then this will give us our minor product. So this is my minor product. So this is how we use Markovnikov rule to predict the major product for electrophilic addition reactions of alkenes. Now the next thing we want to do is to explain Markovnikov rule. Why is it that when my hydrogen is attached to the carbon with more hydrogen and I end up getting my major product? We can actually apply what we learned from electrophilic addition mechanism of my alkene, and we explain Markovnikov rule. So we have our example here. You notice this is our alkene, the same example as before, and my HBr is here. Now the first thing we have to do is we have to decide which one is my electrophile. My hydrogen is less electronegative, so it will be a delta positive charge. My Br is more electronegative, so it is a partial minus charge. So my alkene, because it's electron rich, it will attract something that's electron poor. So my hydrogen in this case, because it's delta positive charge, my hydrogen actually functions as the E+, or my electrophile in this reaction. So when we draw the arrow pushing, I just draw an arrow from my double bond, point to my hydrogen. So one of the carbon, either carbon 1 or carbon 2, will attack the hydrogen, and this HBr bond will break, and both electrons will go to Br. So the consequence of this step is I will form a carbocation, but because my carbon 1 and carbon 2, they are different, so when hydrogen is joined to carbon 1 versus when hydrogen is joined to carbon 2, I'll end up with two different carbocation intermediates. So let's try to draw the two of them. So if my hydrogen is joined to carbon 1, then my intermediate will look something like this. Alright, so this will be my intermediate when my hydrogen is joined to carbon 1. Now, if the hydrogen joins to carbon 2, then the intermediate will look something like this. Alright, so this will be the intermediate where my hydrogen is attached to carbon 2. Now, we have these two different possible intermediates here. The next thing we want to focus on is the stability of each of these carbocation ion, because the more stable the carbocation ion, then the more likely it will be formed and you will end up as the major product. So stability of carbocation ion is dependent on the number of electron donating R groups that are attached to my C+. My C+ is positively charged, so electron donating group will push electron to my C+, make the C+ less positive, so therefore this has a stabilizing effect. So what we have to do is we have to count the number of electron donating R groups that are attached to each of these carbocation ion. So if I look at the intermediate on my left hand side, so this is my C+, and I go and count the number of R groups attached to this C+, what I have is I will have one R group. So this is a hydrogen. Then this is another CH3 group, so I have two R groups. So I have these two R groups that will be pushing electron into my carbocation ion. So I have two electron donating R groups, so it will stabilize the C+ to a certain extent. So this has two electron donating R groups. Now how about the intermediate on my right hand side? Same idea. What we do is we focus on my carbocation ion, and then I go and count the number of R groups attached to my carbocation ion. So this is a hydrogen, this is a hydrogen, and this has one R group which is pushing electron to my C+. So in this case, the intermediate on my right hand side has only one electron donating R group. So this has one electron donating R group. Now if I compare the size, actually this R group is a bigger group than the other two groups, but when there's a difference in the quantity, we focus on the quantity. More donating groups will in total donate more electrons than less donating groups. So when there's a difference in quantity, we focus on quantity, we don't look at size. So if I compare these two, the intermediate on my left hand side will have more electron donating groups, so therefore the carbocation ion is more stable and it's more likely to be formed, so it will end up as the major product. Whereas the intermediate on the right hand side, because it has less electron donating R groups, so therefore it is less stable, less likely formed, so it will end up as the minor product. And you notice when is my carbocation ion more stable is when my hydrogen is joined to the carbon with more hydrogen. So again, in conclusion, when my hydrogen is joined to the carbon with more hydrogen, then it will form a carbocation ion which has more electron donating R groups, so therefore it is more stabilizing and is more likely to be formed, so it ends up as the major product. I hope you have learned something useful from this video involving Markovnikov Rule. If you like this video, please give me the thumbs up, like this video, and subscribe to my YouTube channel for more weekly video lessons. That's all we have for this video. I'll see you next time.